Hi, everybody. Welcome back to Lecture 8. Woohoo! We're still cruising through our Orgoland tour of Orgoland in 3D. How do things look in 3D? And the ultimate question today is, why do we draw our alkane chains as if they're little zigzags as opposed to just anywhere? Is there a reason we do this? So let's see if we can figure that out. And to start with that, trying to figure that out, the easiest thing to do is start with the simplest kind of organic molecule to start figuring out shapes and why they take certain orientations. So if you can, please try to build ethane. Okay, so ethane is going to be the one we're going to look at first, and if you build it, Orgoland will come. And this idea is called conformational analysis. This is going to look at the conformation of such a simple little molecule like ethane. And it's great if you can build it with your model kits, because then you can move it around and look at it in three-dimensional space. So try to do that. Okay, cool. I love ethane down there. Woohoo! Okay, so are the atoms free to rotate? Let's just make sure we're clear about this as we start describing how it behaves in three-dimensional space. It'd be nice to know if these atoms that are all single bonded can rotate. And the answer is yes, they can. So I get free rotation of this methyl group on this side. I can always rotate this methyl group on this side. So I can rotate this molecule anywhere I'd like, not like the double bonds we were just looking at in the last lecture. So this can have lots of different shapes and structures based on these rotations. And that's what we're going to try to figure out is, why do they take their specific shapes and why do they want to be zigzag shaped so much? So to help us understand that, I thought I'd bring in my friend Newman the cat. So Newman is a way to help us start looking at structures on 2 dimensions, on 2-dimensional paper, like the sawhorse drawing here, where you could have a carbon here and a carbon here, and these are all the 3 hydrogens that are in our structure, making up 2 feet and a head. And you can see that we could use wedge and dotted lines. We could turn our line structure sideways to show things pointing out at us, away, out of the paper, and dotted lines into the paper. So you're familiar with, we've seen this. And we've kind of seen this. And this is to make sure that we all agree things like 109 bond angles are still existing for these tetrahedral carbons. Now, what I'd like you to do, though, to help visualize the kind of conformations this molecule can have, and any molecule can have, we're going to want to turn our cat to look straight at us. And so you can see the tail is in the back, and it is sticking off the butt. So in a Newman projection, this big circle is the carbon in the back, aka the butt of the cat. And this little dot in the front represents the carbon on the front. And it's the chest of the cat. Having fun yet? My animal references? You will never look at cats and dogs the same again. Woohoo! All my cats and dogs are little ethane molecules. And in this picture, it looks like all the feet are pointing down in the same front and back. But notice, if I want to represent the feet in the back, I have to just have them attached to the butt, the big circle. So in the end, there's always going to be a big butt and a little chest, and then there's going to be a tail, 2 feet coming off the back of the cat, and a head in this situation, and it's right in front of the tail, so we'll make it a little off center for the head, and a little off center, and a little off center from the front chest for the 2 feet. Even though those feet look like they're perfect alignment, if we put them in perfect alignment, we'd never be able to see the 2 F's on the bottom. And this is called the Newman projection to help us look at molecules down a specific bond and help us understand the orientation of the tail versus the head versus the feet, which will play a bigger role. Okay. So when we're looking at ethane, there are really two extreme conformations that this molecule can take with orienting the hydrogens around the two carbons. And so the easiest way is to actually use little smiley faces to help take your stick and line drawings that you have here. This should be familiar to you, okay? And transfer it to a model that looks like this. And then what I'd like to do is to do Newman projections, take spiky smiley face and pretend you're actually looking down the two carbons from this end. So holding it here and I'm looking down the two carbons. And that way I'm looking down the carbon-carbon bond and therefore able to create the Newman projection for this eclipsed conformation. And therefore model kits are really great at this, because if you're drawing it like this, the only thing you need to do is build the molecule like this with two hydrogens sticking out as wedges, two hydrogens in the back here as dotted lines, and then turn the molecule towards you so you can look down the carbon-carbon bond and literally see that all the hydrogen atoms are eclipsed to each other if I'm looking right down that bond. Okay? So this is what the Newman projection would look like. I'd have a big butt in the back here with 3 H's coming off, as you can see, and the front carbon has the lines with 3 H's coming off. So this is the highest energy conformation that this molecule can obtain, and we'll talk about why in a second. The other extreme conformation is if you were to take this molecule and rotate 60 degrees, just get these hydrogens away from each other. So my other little smiley face is going to be looking down here and going to create the next Newman projection. Take a second and see, can you show me the Newman projection that would be created for this carbon-carbon bond? What would yours look like? Pause, please draw it. Give it a shot. Okay, let's see what you came up with. Does your Newman projection look like mine? All the hydrogens are off by 60 degrees. So they're no longer eclipsing each other. They're no longer overlapping. They are in their own space. And it really didn't matter. You could have drawn, again, this is a representation basically not necessarily of this Newman up here. You know what? You're right. If I were to draw it exactly as it's shown up above, notice that the first carbon I'm looking at has a hydrogen that's pointing down. Oops. A hydrogen that's pointing down. Okay? And the back carbon has a hydrogen pointing up. So that would be this one and this one. Those two hydrogens are in the plane of the paper, here and here, and the hydrogen is pointing down, and the butt carbon has a hydrogen pointing straight up. And then what you want to do as you're looking at this is look to the right, and literally to the right of this look where the smiley face is, you are looking to the right side of the molecule, and those are the dotted line hydrogens going to the back of the page. And if I'm looking down the page, then all the wedges on my diagram are to the left. So literally be spatially oriented on your piece of paper to see that dotted lines, if you're looking at it from this point of view, dotted lines are to the right and wedges are to the left. Okay, so my final Newman is going to have the front carbon with these two hydrogens here and here, and the back two hydrogens coming off the butt are going to be here and here. So notice these two Newman projections are essentially equivalent, but just from different points of view. They both have the hydrogens 60 degrees away from each other as you look down the carbon-carbon bond, okay? And this staggered conformation is much more energetically favorable than the eclipsed one. How we doing? Okay? Bring your questions and your models to our study groups. This is very, very important. It's the easiest way to visualize as you're starting to get this. So this staggered conformation is more stable by 2.9 kilocalories per mole. The other one, eclipsed, is awful by 2.9 kilocalories per mole. But what I want you to remember is around me in the room is 20 kilocalories per mole. So that means the energy in this room allows me to rotate through all of these possible conformations, staggered eclipse, staggered eclipse, staggered eclipse, because there's plenty of energy in the room to do that. So this molecule has no problem rotating, okay? As opposed to a double bond, no rotation. So let's get more complicated. See if you can take your ethane and please build the butane chain for me. Okay, here is the 4-carbon butane chain as pictured down here. Here, yes, over there. Okay, so please take a moment and build this butane chain for me. And now, please take this smiley face guy and look down the carbon 2-3 bond is what this question is asking. And try to hold your model in the least stable conformation you think can happen when we rotate it all around. When you're looking down that 2-3 bond, which conformation did you come up with? And one of the things you're going to sooner or later have to do is figure out on the butt carbon, the 3 bonds coming off the back and the 3 bonds coming off the front carbon, you have to start prioritizing who's the bigger group. Who's the bigger group is easily determined by using those same 3 dead chemist rules that we used for determining highest priority in E and Z. Please use those rules again, meaning off the front carbon, I go to a carbon, a hydrogen, and a hydrogen. Therefore, this carbon has a higher priority. And please try to not make this eclipsed. This carbon cannot be eclipsed. That would be bad. If you happen to eclipse some hydrogens, not great, but better than eclipsing carbons. Okay, let's see what you came up with. Here is the 4 possible conformations that you could have written as Newman projections. Which one did you have, or which one do you think matches your structure from your model kit? So take a second, circle the answer, because I'm going to show it to you. Ready? Okay, here it comes. And the correct answer is, according to Newman the cat, having everybody like the tail and the head eclipsed is the worst scenario you could possibly have. So this is the Newman projection looking down that 2-3 bond. That would be the highest energy conformation. All the other ones are possible still, and there are some others that are eclipsed, and some that are staggered, and some of these that we see here are not all the same energy as well. So as we get bigger molecules, we're going to try to look at different things. So now some definitions. When you have these methyl groups on the same plane, the head and the tail looking right at each other on the same plane, then what you end up getting is similar to our alkenes. You get steric strain. So it's similar to having a cis alkene or a Z, Zame-Zide alkene. Ooh, I worked that in here even. Woohoo, Zame-Zide. Okay, so even having these 2 methyls on the Zame-Zide, they'll cause steric strain, meaning atoms bumping into each other. But also, now that you see in the Newman projection, the bonds are all lining up with each other, meaning the electrons in these bonds are repelling each other as well. That is called torsional strain. So we don't like when bonds are overlapping with each other. They are full of electron density and they will repel each other as well. So an eclipsed molecule is not very happy in a lot of ways. It has steric strain and torsional strain. Okay? Couple new definitions for us. So let's try this one. Take your same butane. If you need the model kit, go for it. If you don't, since model kits will not be allowed on the exam, no model kits on the exam, we're going to have to start visualizing these things in three-dimensional space. Pick which Newman projection you think shows the lowest energy conformation, looking down the C2, C3 bond of butane. Take a second, pause. Welcome back. Ready? Let's see if you got the same answer I did. I got B, and this gets its own name for this. It's not just staggered. No, this is so awesome. Putting the head and the tail on opposite sides of the Newman projection. Having the head bend down like it's eating or licking a bowl of milk with the tail straight up in the back puts the two methyl groups anti to each other. Anti is very much like E and alkenes. The two highest priorities are on opposite sides of this molecule. So if you have this molecule and you take it and you put these groups anti to each other. So here's one methyl sticking, oh, let's do, there we go. The head of the cat is down. The tail of the cat is up. And if this is the lowest energy conformation because there is no eclipsed bonds, and as you can see, the two biggest groups are far, far away from each other, so there's no steric strain, there's no torsional strain. This is the happy nirvana that this molecule wants to exist in. And turn it sideways, and what you'll notice is it looks like a zigzag. This is why our alkane chains like to be drawn as zigzags, because zigzag creates the anti-conformation, which is the lowest energy conformation for your molecule. Okay, kind of cool. There's a reason for everything. Whoa, what's gauche? Gauche? Oh, who's gauche? Am I gauche? Gauche? Is it bad to be gauche? In Orgoland, this is what gauche is. It is not eclipsed. So no whining from anybody. It's not as bad as eclipsed, but it's not as good as anti. So this is gauche. Gauche is an interaction where you have the two largest methyl groups are not anti to each other, but they're also not eclipsed with one another. So the two largest groups are just separated by 60 degrees. And this is called a gauche interaction. Okay. Now, keep in mind, this is what this molecule would look like if you turned it sideways and drew it on a piece of paper. Again, these are all really, you could rotate this bond and draw this molecule in lots of different ways. But notice, most importantly, this methyl is in the plane of the paper, and this methyl is a little wedge sticking out at you. Okay? And that's the key. They are not on the same plane. Okay? But they still look like they're both on top of this molecule. So that means they are both on top, and there's still a bottom, and they're on top but 60 degrees apart from each other. This is what gauche is. Okay? There's a little steric strain between these methyls, so it's not great. That means it's not as good as anti, which means I kind of don't have a happy face yet. But notice there's no torsional strain at all. There's no bonds that are eclipsing one another. So this is still much better than, oh, whatever they did to make that kid cry. I don't know, I'm sorry. But it's still a little better than that. Now, I tried looking for a cat that was in a gauche conformation. This is not an easy thing to do. If anybody can find a head and a tail that are in gauche with the feet, one sticking up, one you can, this sort of, I give. Okay, so this is the closest I could get to a gauche conformation for a cat. Maybe if you have a cat at home, can you train it to sit in a gauche conformation and take a picture for me? I would really appreciate it. Or even a dog. I'll take any animal with four legs and a head and a tail, and let's see if we can get the gauche conformation. All right, here's the summary of the whole thing. And these angles that are between the actual groups have a name. These are called dihedral angles. So right now, this is in the eclipsed conformation and showing that it has a very high energy relative to all the other conformations that follow by just turning this molecule 60 degrees at a time. So when you turn it 60 degrees, you drop it down to a gauche conformation, but not the best gauche. And then you rotate it another 60 degrees and you get back to an eclipsed, but not the worst eclipsed. So this molecule is constantly rotating around, and then it gets to its anti after a few rotations, a few 60-degree moves, which is nirvana, and our zigzag, and that's the lowest energy conformation. And then as it continues to rotate, it goes back to the worst case scenario. Okay, so this is called an energy diagram for the rotation of the butane chain as it goes through all of its dihedral angles around carbons 2 and 3. And it summarizes every conformation that butane has, hexane has, any molecule other than ethane is going to be able to go through these rotations and have these conformations. And now they have names. We have eclipsed, gauche, and anti. And you should be familiar with which one is the worst, which one's the best, and which one's kind of in the middle. Okay? And so in room temperature, we've got this conformation. This is also showing you that even the worst conformation is 4.5 kilocalories per mole worse than the anti. So even though we like to write our molecules as zigzags, this molecule is constantly rotating in and around and creating worst to best to worst to best, constantly moving around the single bonds at room temperature. Okay? That's the take-home message. So what I'd love for you to do for our study groups is the following. Please draw the Newman projection down this red bond from our perspective of our little smiley face people. Okay, looking down that bond, draw the Newman projection as is, then rotate and redraw and create the new Newman projection if needed to show the lowest energy conformation possible. So you will have 2 of these. Try doing it without your molecular model kits. The more you can practice without them and then maybe confirm with them, that would be great. Always practicing anything that we can do, to continue bringing back stuff from old, to keep making it new. Try naming these compounds. That would also be really helpful. And in the end all be all, please come to study groups with pictures of your answers. Okay? Pictures of your answers that you can insert, copy and paste directly into your Jamboard before I even show up. Everybody needs to try these. I don't care how weird your Newman projections are, but don't come to our class and our study groups without some actual pictures of hand-drawn Newman projections for these 2 situations. Then we can talk about them. Okay? All right. Coming up soon, next lecture, we go from alkenes to alkane conformations, and then the final piece of chapter 6 is looking at rings. Okay? Ring conformations are really fun because I can tell you right now, this is a nice happy 5-membered ring, but the worst part about it is, notice if it's planar, all the bonds are in the same plane, this would have extreme torsional strain. And therefore, it does not want to be like this, even though they look like the bond angles could be 109 or so. This is awful. So we're going to look at how this molecule actually changes its conformation to relieve some of that torsional strain. and then we'll look at cyclohexane as well. So come prepared to add a carbon and make it bigger. We'll start with models to help things make it easier, and then we'll leave the models aside as our mental acuity of shapes and images of shapes gets better and better over the next few days. Okay? All right, as always, please feel free to email me questions, and I hope you like this lecture. I love talking about shapes. Okay, I'll see you soon. Bye.